Okay, can you see it?
Yes, we can see it.
Okay, good. Okay, we'll start. Good morning, ladies and gentlemen. It is the last day of these five workshops. It is a quite intensive program, and we talk about the multi-hazard affecting dams and other structures belonging to large dam projects. And I would like to present here in detail the case of the Cepheid Root Dam in Iran, which was damaged during the magnitude 7.5 Manchil earthquake of June 21, 1990. And okay, this case is probably the worst effect up to now which has been observed at the concrete dam. So therefore, I like to present it as a reference, and it has also affected many other, let me say, structures and components of a large dam project. Okay, the dam I'm talking about is in Iran. Here is Iran. Here is the Caspian Sea. Okay, Pakistan, Afghanistan. Okay, India is not there. But the enlargement here, it is just in the south of the Caspian Sea and a little to the west of Tehran. If you look into this map here, we see the dam is here. It is located at the, there two rivers are joining. This here, this is the Caspian Sea, this is Tehran. It's about 150, 200 kilometers from Tehran. Okay, so that is the location we are talking about. And the mountain range, which is where this dam is located, is called the Alborz mountain range. Also, this area is quite different from other parts of Iran because close to the Caspian Sea, you have the effect of this Caspian Sea. You have a higher humidity and the land is green, whereas in other places, the land is much less green. Okay, this is a map of faults which are there, and we can see the Cepheid Root Dam. Yeah, it comes. Okay, we see here the location of the Cepheid Root Dam, and there are in Iran. You have everywhere. You have some fault, and there is a fault also close to this dam site. It is not really marked, but you can see here this boundary is a boundary of the reservoir. So the fault here, according to this map, is actually passing at almost at the dam site, a few hundred meters or a few meters from the dam site. Okay, there was this strong earthquake in June 1990, and I was a member there of the International Reconnaissance Team, which at that time was called by President Rafsanjani. And this is a way, we went there about 10 days after the earthquake. Okay, we were able to arrive in Iran. It was not so easy at that time, but this is on the way to this dam site. You see some debris here and there, some village here and there. I would like to mention that this was probably the strongest or the most destructive earthquake in the last decade of the previous century, in the 1990s, with 40,000 people killed, actually very close to the dam site, in cities close to the dam site. Okay, you see here, it is a few kilometers from the dam. This was a village. Actually, nothing is left here. All buildings are destroyed. Therefore, the huge number of people killed. Okay, these are just a few photos which I took when we traveled to the dam site along the roads. Okay, basically these structures, you know, they are a poor quality structure, and I would say mainly non-engineered structures which collapsed. Okay, now looking into the dam, the Cepheid Root Dam here is a buttress dam with a height of about 105 meters, and we can see here is a powerhouse. We see here the spillway, so-called Morning Glory spillways. There are two of them, and the water is released here. And there is another on the left side, and there is another intermediate level spillway, which is shown here. So I will refer to these structures, and there is also a road here, let me say, passing above this intakes of this Morning Glory spillway, and the road passing here across the dam, and here a few meters, and then going into a tunnel, and here also some road at the right bank, which I would like to show. Here are also the intakes for the power intakes, and here are 7 bottom outlets, or we can call low-level outlets. I use this term low-level outlets. Some people in Switzerland, we talk about bottom outlets, but here they were also called irrigation outlets. So there are 2 of these outlets. And now this Alborz mountain is in an area of high seismicity in Iran, like the other mountain range, the Zagros mountain range, further to the west. Okay, this is a typical cross-section. This is a buttress dam. I would say this dam, it was built in the 50s, 60s. Buttress dams were somehow popular for some time. I would say because people thought they could save some concrete. Today, I would say you do not build buttress dams, or only in exceptional cases, because the manpower also for formwork and so on, it is too labor intensive. Okay, we see here the dam with some monitoring equipment. There are also some pendulums, okay, some plumb lines in order to measure the deformations. So there are a number of instruments which are shown here. I do not go into the detail, but with the plumb line, you have the advantage, of course, based on the results of these plumb lines, to see what are the deformations, the remaining deformations after the earthquake. There are also some joint meters on the surface to see if there are any relative displacements between different buttresses. Also, there's some control galleries. You can record the relative displacements there as well. So that is the overview on the dam. I must say this type of dam, it's not being built now, but it has been popular for a few decades. And this dam is basically a representative for the behavior of gravity dams. Also, it is not really a gravity dam. We do not have such similar information for a gravity dam. I would also like to refer at the downstream phase here. We have this kink, and I will refer to that. This is the web of a buttress, which is shown here. And this kink here is somehow a critical point. This is the head of the buttress, and we have here a location. Let me say this detail I will show when at the downstream phase of a dam, which was somehow one of the critical points in this dam. Okay, so this is just a picture after the earthquake, because the dam was damaged, and if the dam is damaged and the powerhouse was out of operation, it was severely damaged. So therefore, to control the water is basically only possible through the spillways, but the water level was below the intake of the spillway, and there is this, I mentioned on the left bank, we have this intermediate level spillway, which I have shown before, which I will also mention then. But what you can see here, after the earthquake, they opened bottom outlet or low level outlets, irrigation outlets, in order to lower the reservoir, because there were some damage here in the top part of the dam, which required basically lowering of a reservoir. The lowering of a reservoir was only done a little below the damaged zone, because the water in the reservoir is really needed there for irrigation, because most of the rice in Iran, the local rice, is planted in this region, is near the Caspian Sea. The other parts are not suitable for rice cultivation. Okay, we see here a photo from a left bank, yes, from a left bank to the dam body. Maybe you can see here already some water leakage here, some leakage here, and so on. Okay, this is a view from the upstream phase of a dam. Here once more downstream with the powerhouse. It is a relatively small powerhouse. And you can see here, I will show that on the next one. Here we have, let me say, the switch yard, and faintly you can see here on the ground, this is actually the first transmission tower. Just from the powerhouse, first transmission tower, and of course it is clear if the transmission tower fails, the power generation will be closed. Okay, power plant will be shut down, and we see here also still the irrigation outlet in operation, and this is on the left bank, the chute of the intermediate level spillway. Okay, this is the operation of the irrigation outlet. As I said, this is just after the earthquake. And here we can see some of the leakages. This is again this intermediate level outlet. You can see some of the leakages here, and you see the leakages along horizontal lines. These horizontal lines at different elevations here show that this has been basically a lift elevation. The lift elevations used during construction of this dam was typically 2 meters increments. Okay, we see here a more accurate from inside. This is a web of the buttress, and you can see here that the water is leaking here along the whole the whole lift joint. It means that this joint here, a crack has developed along this lift joint, and this crack developed not just 1 meter deep, it developed through the whole dam body. Okay, we see here this is a contraction joints, and here we have water stops, and here this is the adjacent one where this crack doesn't really manifest in a way we see in this buttress. Okay, this is another view which shows it more clearly. Okay, we have here web, we have here some leakage here, here, okay. And it all indicates that we have basically cracks propagating from upstream to downstream. So the dam is completely cracked. Okay, that is a lesson number one we could learn from here. And the lesson number two is that these cracks developed at lift joints. So these lift joints, temporary joints, are actually weak elements in concrete dams, because if it is not perfectly cleaned, let me say, before the next batch of concrete is placed or the next lift is placed there, it forms a weak interface, and it is obvious if you have some cracks mainly develop along such weak interfaces and not in the parent concrete. But in the analysis, of course, people assume the dams to be homogeneous, but this is not the case. The lift elements, the lift joints are actually weak, some weak points. They would need special attention. Okay, now the critical damage which has occurred is shown basically on this diagram or on this plan. We have here the web, and here the head of this buttress, and we have some cracks along this interface here between the web and the head. And in addition, we have here some horizontal crack along a lift joint. And when we have this crack here and this crack here, this wedge is about 3 meters high, 3-4 meters high. It became separated, basically separated by 2 cracks. So I will show them that, and we have some crack developing here and then some crack developing further here. In addition, there were some old cracks from the time of construction. They have nothing to do with the earthquake. They are basically shrinkage cracks from the time of construction. So you are not disturbed by these cracks here. The effects which occurred here in the top quarter, if I may say it, in the top quarter of a dam. So that is the situation. To have a better understanding, okay, here we have enlarged that. Sorry, I said 3 meters. This wedge is actually 4 meters high. This is a better detail showing the cracks which developed here in the vicinity of this kink and in the vicinity of this interface between the head of the buttress and the web. And since this crack here, if it is fully cracked, okay, this here basically moved. So this wedge here moved a few millimeters, or let me say about 2.5 to 3 centimeters. We can see it, but to understand the photos better, you would have to look into this detailed diagram. And again, as what is shown here on this dotted line, these are the lift elevations. Typically, they use this 2 meters, and you can clearly see we have a crack along this lift elevation, and we have crack along this interface. It's also a cold joint between the web and the head of this buttress. So we see here on top of one of these wedges of his buttresses, it was quite heavily cracked, as we can see here. Okay, this is this location here. we have this kind of cracks, which I show here. And I mentioned it already previously in a discussion of stress concentration. It is clear that if you have a sudden change in slope, you have a kink here. If it would be theoretical a kink, a sharp kink, the stresses here very locally would be infinite. If you would do just a finite element model with a sharp corner, you would, or you would do the analysis, elasticity of such a body, you would get here infinite stresses, but we do not really have in practice the theoretical sharp corner. It is still some let me say it is not a sharp kink, but relatively sharp, but it creates then this stress concentration in this zone here, and this zone then are the points where cracks preferably occur. Okay. We see this is this block now from below. I must say, I think I took that photo also. I would just like to mention here, this is this offset. This is this view here, looking from maybe from here to up here, and you see this offset here. So this wedge above here, which was separated by a horizontal crack and a crack along the interface between the web and the head of a buttress, was basically free. And during the earthquake, during the shaking, this wedge here was moved downwards, and you can see the offset is about 3 centimeters. Of course, if the earthquake would have lasted longer, this offset would be more. But it is quite critical, because if some part is missing, is not carrying, I would say, if I just go back here, okay, if some parts here are missing, this wedge is missing, suddenly no longer carrying. This structure here gives some more kink here, and it gives unfavorable, let me say, stress concentration there and redistribution of the stresses in this area. And it is very unfavorable, because this is, again, if you would say, this is now a sharp corner with even larger stress concentration. Okay, we see here from a neighboring block, you know, this one here, it does not go sharply along this joint between the head and the web, but you see the crack here more or less follows this portion. But it originates here again near this kink, which is this location of stress concentration. So that was a view of the downstream phase. Now, if you look in the upstream phase, the crack also showed, or several cracks, those which were leaking, there are some cracks which went through all the buttresses from left bank to the right bank, and they were also along, as you can see it is along this lip joint. I must say this is now about 10 days after the earthquake, because at the time of the earthquake, I thought the water level was here or here. It was only slightly above this crack, and because the water level was only slightly above the crack, the water pressure was not very high, so the water was not really passing through this crack under high pressure. So it was only seeping there, and you could see the kind of leakage, which I've shown in a previous photo. But here, I think it was still a time the water level was slightly reduced. But as I mentioned already, the dam owner, we were asking for lowering the reservoir more because we were concerned about the safety of the dam. But the dam owner was against it because they had different objectives. They were concerned about the irrigation, the availability of the water for irrigation. Okay, we see some of the cracks in the downstream phase again. And of course, the crack is only small, but at the surface, okay, it moved slightly back and forth. We have this falling of concrete. This is not the width of a crack actually here. This is just at the surface falling of concrete. And similarly here at the upstream phase, this is near the intake. It also looks like this crack is very large, but this is just falling at the surface. Okay, so usually we will have some spalling, but I would say the crack here it typically is only in a range of millimeters. It's very small. Okay, we see here also at some intakes, we see these cracks basically along this lift joint. So as I mentioned already, you have to assume and people are not really considering it in their finite element models that actually cracks, preferably if you have an overstress, that the cracks will preferably develop along lift joints. Now, if we look on the dam crest, due to high stresses between adjacent cantilever or buttresses, we have here also, you could see, we have a longitudinal crack on the dam crest, and we have here at the joint of two buttresses, we have shearing off of some concrete. It means we had high axial stresses in this direction. This here is a joint meter. Okay, on all these joints, we have these joint meters. So it was possible to measure in a simple way by these bolts the relative displacement of these adjacent blocks along all blocks. We see here some more. This is another one. This again is joint meter. We see here some cracks. This is a crack in the top of a dam, which is an indication, as I said, of the large stresses in the, let me say, in the across river direction. Usually, if you do the analysis, you do the analysis only for this kind of blocks in this direction. But during earthquakes, of course, you also have the action in a cross canyon direction along the line, along the dam axis, as shown here. Okay, this is this typical cracks at the on the dam crest, indication of shearing off due to high axial stresses. This is a condition now in the galleries. There are different galleries. This is a joint gallery, and this shows the condition of the joint between two adjacent buttresses. And we could see here, also there is no measurement here, but just optically we can see that some small movements have taken place because this concrete or mortar which was placed here was falling down. This is between block 13, 14. This is, okay, I should separate here. This is another joint, 15 and 16, and you could see that some relative movements of adjacent blocks have taken place, which is manifested by this, let me say, spalling off of mortar, and you could see it on the ground, on the floor of the inspection gallery, that material was falling down. Okay, this is on the left abutment. There is some fill also, and you could see we have some deformations at this, let me say, platform. This is on the left bank. Then there is this parapet wall, parapet walls at the downstream and upstream face, and these parapet walls are, what shall I say, non-structural. So therefore, you could see this parapet wall. It had some reinforcement, but its center of gravity is also quite high. So, and on the top of the dam, you have also an amplified dynamic response, actually, which is larger than the ground acceleration. So it caused here some of these elements here to almost fall down. As you can see here, the reinforcement was also fractured. So to protect them, basically, just after the earthquake, these deformed parapet walls were moved in on this side, that they could not fall down, because down was the powerhouse, and if it would fall down, it would damage actually the roof of the powerhouse. So the parts here, as you can see, they were saved. This is just walls which were almost, people thought, could fall down, so they put them back, they stabilized them. Not that we have some further earthquakes, because when we were there was still, I think, some aftershock. We stayed about 50 kilometers overnight, and people were still staying, let me say, out of their houses. And I think there was still an aftershock of about magnitude 6 when we were there. Okay, this is a detail of this parapet wall. Yeah, okay, we have this big joint and this reinforcement here. Okay, as you can see here, is already fractured. So therefore, it is quite unstable. Therefore, this parapet walls have to be saved. There is one in the upstream face above the intake structures, and you could see here this actually overturned already, but it did not really fall into the reservoir. You can also see it is quite wavy. It's from, let me say, thermal effects. It was locally a very strong wind. It was impossible to take a boat and to inspect actually the upstream face, because the wind was so strong, maybe 100 kilometers. So nobody really dared to go, for example, in the afternoon. You could maybe go in the early morning, but to inspect the dam from upstream, because it could not be done. Okay, we see here is some more parapet wall at the upstream face. This is now a fissure. It's a crack here because the dam is located on two geological formation, I think andesite and basalt, and at the interface there was already a crack. This is a bottom gallery here in the buttress, in the buttress head, and you could see here that through this crack, as I said, this crack already originated from, it's an old crack from the time of the construction here because of the geology, but due to the ground shaking, let me say, this crack was slightly moved, and the material which filled this crack was basically washed out. And here at the bottom gallery, we have, of course, the high pressure. We have a head of about, let me say, about 80 meters. So the water is splashing in under high pressure, opposite to what I have shown before, where the pressure was very low and the water was only seeping in. So for protection, I have put here some corrugated sheets here when we walked through these places. Okay, now are these intakes for the spillway. These are these so-called Morning Glory spillways. We have here one, and here we have the second, and there is also the road which I've briefly shown, which passes by. It is quite steep, and you can see there is a platform just above this intake into a spillway. Here another platform, but you can see here these are already there are a few blocks here. These blocks are quite big, are 5-6 meters high, and here even higher. It was just above this intake of this spillway. Here we have some others. So most of the rock falls which occurred, I think it was also reported that during that earthquake there were about 10,000 of rock falls. So during a strong earthquake, you have to assume there will be many rock falls. I mentioned already Wenchuan, where some reports claim 200,000. The other one in a relatively recent one in New Zealand, it also caused 100,000. So it causes really many rock falls in mountainous regions. Okay, I will show when that. Okay, there were some smaller, let me say, stones which jumped over that and fell into this spillway, which was not really a problem. But the big boulders were kept here just by this platform above the intake of this Morning Glory spillway. So we see it how it looks. This is this platform above this Morning Glory spillway. This is this intake of a Morning Glory spillway. We see here some of the boulders which moved in, and there are some stones here, a smaller one which shows there are some stones. We could also see on the surface some small impact. Some smaller stones actually fell into this Morning Glory spillway. Okay, that is the spillway. Now let me say a few words about the intermediate level spillway on the left bank. This is just the outlet structure of that spillway, and we would like to look here. These are the outlets of the Morning Glory spillway here. This is from the intermediate level outlet, and these are some of the buildings here belonging to the power plant. Okay, we'll see that most have been basically fully destroyed. This building here is still okay, and people assumed that basically the epicenter of the earthquake was about here. You know, it's just a few meters, about 500 meters from a dam site, or 800 meters. Okay, that when we were there, it was claimed, or shortly after we returned, I must say it was claimed that the epicenter basically was right at the dam site. So for magnitude 7.5 earthquake, so the ground shaking was very strong. So now let's look into this intermediate level spillway, and we can see here, yeah, there is also some material falling into in this channel here, in this chute of this intermediate level spillway, and here another photo showing. Okay, this is an earlier one which shows that these gates here are leaking and some water was coming out. And when we were doing our mission, I must say we were spent about 5 days there. It was not possible actually to enter this, let me say, to enter here this intermediate level spillway because it needed some special safety equipment which was not available. But with intermediate level spillway, you see here, it has a radial gate, and this radial gate was blocked. We asked the dam owner to operate the intermediate level spillway, but they were not ready to do that. They refused that, so therefore we could not, when we were there, we could not really check the condition of that. But then later on, we were informed that, and we got some not so good quality photos here, which shows this radial gate with the arm, and that this arm basically was deformed, and this caused additional leakage. And you see here, I think there is this part which was replaced, which is cut here. And you can see here, this is a horizontal reference line. And if you look this arm, you see it buckled, it deformed. Yeah, it's quite some deformation which occurred here. And it is clear if this arm is deforming, most likely you will not be able to operate the spillway. Now, this high, let me say, high forces, axial forces, which cause this local buckling of the spillway, were basically due to the hydrodynamic pressures. Okay, some people have some problems with hydrodynamic pressures or claim they may not exist or have not shown damage due to that. But in this intermediate level spillway, which there is a tunnel here about 50 meters until the location of this gate, there you have actually an increased hydrodynamic pressure, and this hydrodynamic pressure, it must be this hydrodynamic pressure which caused then this buckling, inelastic buckling of this arm, which is, let me say, kind of a unique experience. We see here, because of this deformation, so also it would not be possible to operate this spillway. And we can see also this leakage. Also, this leakage is just an indication that some deformations have taken place, and also the ceiling, of course, were not maybe well maintained. Okay, this is some more photos from this intermediate level spillway. We see here some leakage occurring here at the corner. And we see here, when if we take away this gate, this is another gate. Let me say it's not the intermediate level. There is, of course, if you look here, the ceiling here is deficient, and here it is missing, causing this kind of splashing of water. Now, this dam is used for irrigation purposes. It's an important project for irrigation, as I mentioned. So there are some irrigation canals, and you can see here the lining of this canal, concrete lining. It's also basically it failed. So the irrigation system here is also has also been affected. Moreover, here is a diversion there, also for this irrigation system, which is about, I think this was about 20, 30 kilometers downstream of the dam. And for operating these gates, it is, let me say, important for the hydromechanical engineers. You know, for gate operation, you use different systems, but you have here many openings. How does it come? Okay, finally, somehow. Okay, you see here, for operating these gates, you have counterweights. There is counterweights. As I said, there are different systems. but this is a system I used at that time. But you could see that after the earthquake, this is taken, I have taken after the earthquake, here this counterweight is down, here there is some stop lock, but counterweights being down, 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 down here, because the opening, all these spillway gates had the same system, so basically all had the same failure mode. So this counterweights in this part, as you can see here, they all fell down. The problem is, yes, if you have this multiple gates, if one fails, it is not redundant. You know, it is the redundancy concept, which is often used, you know, if you say to control some hazard. In a case of earthquake, it doesn't work because all redundant systems basically are subjected to the earthquake action at the same time. So if one, let me say, if the system actually has one deficiency, basically it affects all these openings. As you can see here, it is an interesting example. Okay, some somehow are still left in place, as we can see here on this side. But on the other side, they are basically all falling down. Now here, I'm not sure why we have these stop blocks. Okay, maybe there was some maintenance work going on. Okay, now as it is in most cases, there was a seismic station there, and as happened here, when the earthquake occurred, people said the seismic instruments, they were not placed on a dam body, they were placed in a foundation, were sent for maintenance to Tehran. Okay, so there are no instrumental data available of this ground shaking. The only instrumental data, if I may say it like that, is based on these pipes. Okay, this is the location of the epicenter. What people said, this is basically the epicenter. So there was this heap of pipes, and during this strong ground shaking, it moved in this direction, and it moved perpendicular to that, because it allowed, they rolled in this side and they rolled in out of plane here. So it was possible, but I had to leave that photos in Iran, because when we left the country, we were said it was not allowed to take along the photos. Okay, I still managed to take along about 2 film rolls, but about 10, I must say, I had to leave there. But I just wanted to say we could basically, based on here, by looking here on the surface of this pipe, we could see basically how it moved. Those are quite interesting. So one could finally get some, let me say, information on the deformations which have taken place. Of course, nobody has done a reanalysis of that. Okay, but this is just the epicentral region, and when I was walking here, I was disturbed that the soil looked quite strange, and I had no explanation. But afterwards, when it was said the epicenter was here, I think there were kind of signs of also it was gravelly, like some liquefaction effects or some deformations effect taking place. But afterwards, my colleague here, Iranian colleague, his interpretation was that this fault, one of the fault, passed here on the left bank, and it passed here through the dam. Was his interpretation. And when I was there, we did not really see that, but this was his He was in charge of a rehabilitation of the dam afterwards, but in this area there were cracks in the access road, and you could see these cracks indicate that, yeah, a fault or a secondary fault, some parts of a fault fractures crossed this road at some locations. Now, what I have shown just before in the Morning Glory Spillway, these are some of the boulders which came down and which were stuck, unfortunately, just above the Morning Glory Spillway is just below. Unfortunately, they did not fall in, but they killed some Revolutionary Guards which had a small hut here under some of these stones. Okay, and we see here there is a tunnel continuation goes in, the road goes through a tunnel. Again, this is a picture which I have shown, which is this is just one day after the earthquake. The one is already 10 days later. At that time, nobody could really pass. But you see here, this is this big boulder I've shown before, which is just above the Morning Glory Spillway. It damaged these railings here. Okay, on the other bank, it was on the right bank. The dam is to the left here. It's just platform leading to the dam body. You see it is basically the whole road. You could not move. The road is all littered by rock falls, so it's not really possible to move in here. There's plenty of rock falls. Okay, this is the same location. This again is a dam, but you see everywhere rock falls here near the dam body, again rock falls. So a typical feature, I must say, in dams in mountainous regions is a rock fall. I would like to refer once more. Here are these two Morning Glory spillways, which I mentioned here, with some blocks just above these platforms. You see some of these blocks are not small. Yeah, it is about 10 meters high, okay, which fall. And here you could just see part of a Morning Glory spillway. It is very, very close. So one has really to look into those. These boulders are not small. And this is the transmission tower I've shown before, the first transmission tower from a powerhouse. It was hit also by a stone. I have shown it also before. I would say it is not a big one. It's maybe 2 or 3 cubic meters is enough basically to destroy this transmission tower, which was not protected. I must say we have in the mountains, in India, you also have this rockfall hazard, and I think usually you would protect these towers against some rockfalls. In our case, we would protect them against avalanches. But here, okay, it would be quite simple to make these transmission towers safe. Okay, again, this an access road downstream of a dam. Basically, it was not possible to go there. The first people who went there, they went there actually by a helicopter. Okay, some more rock falls near the dam crest. The platform here to on the left side of the bank of the dam. This is now what I've also shown, the portal, entrance portal of the tunnel. And you see, again, because some people also asked, what is the seismic hazard of underground structures? I would say the seismic hazard of underground structures is basically portals. Okay, portal zones. And as you can see here, come some stones down here, and they have destroyed here parts of this portal. This was the act. This is already, they have cleared that already. I must say the Iranians, they were extremely efficient with, let me say, with clearing work because this was 1990. This was just at the end of the Iranian war, which ended, I think, in '88, and people were, let me say, experienced, if I may call it like that, with dealing with great catastrophes like that. With 40,000 people killed, they had this kind of large number of deaths already during the time of a war. Okay. You see here there is an oil pipeline. It is a small oil pipeline here, and when we passed, it is a petrol. It is not crude oil. It is a small diameter. It was punctured by some rocks, and due to the puncturing by the rock, you see here, some of the oil is still splashing out here from this pipeline. It's just probably just a 10-inch pipeline. Okay, this is a powerhouse. Downstream, you see here the joint between units. This is a typical structural problem that we have plastic hinge here at the end of the columns. When we have a large, a very stiff cross beam. For seismic safety, actually this failure mode is not good. It should be opposite. Basically, we would usually design structures that plastic hinges will develop actually in beams and should not develop in columns. These are dangerous. Okay, this is inside the powerhouse. I've also shown that a couple of times. But it shows, yeah, that you also have to take care in the buildings of the control center, the control room. These infill walls, you know, it just disintegrated. You have some light falling on some panels. And I would say if these panels are crucial, then this can cause further problems. And this power plant has been attacked a couple of times by the Iraqi Air Force. You see here there are still some sandbags here to protect this control room. This is just 2 years after the war. Also, the switchyard, I mentioned that already. The switchyard, you have to take into account, let me say, switchyards are basically designed by electrical engineers. And I must say the electrical engineers, they are not experts in earthquake engineering. So somebody actually has to look into that, somebody who understands the dynamics, because we have here, as you can see, we have these ceramic insulators located on these freestanding columns, and under ground shaking here with a high center of gravity, they overturn. This would be one failure mode. So therefore, anchorage basically of the equipment in the foundation is very essential. I must say, if you have equipment, the main problem in order to get safe equipment is the anchorage into the foundation in structural walls, or to attach it to structural walls or structural foundations. Okay, but here it is already high. This didn't fail as such here, but we see, I have to assume that this part of this switchyard is founded on fill material. And as I mentioned already yesterday, fill material, if you use seismic building codes, you will see fill material is the worst foundation of any structure. Okay, you see here, this is a part of the switchyard with filled, and we have then here some local slides at the end of this switchyard. So this is this fill, which is quite vulnerable under seismic action. So it has to be taken into account. in designing this equipment. If you are on fill material, you need basically stronger anchoring, and if it is on the rock, you could use lesser, but you should basically take into account usually just the worst case. Okay, this is just below this switch yard, showing you some damage. You see here some buildings on the premises of this power plant. It collapsed. There is some transformers. Transformers are on the rails. If they are on the rails, they must be fixed. We see here it has been derailed. There is some more which have been derailed. Again, they have been attacked by the Iraqi, so there are still many sandbags around this critical equipment. Okay, another one which derailed, and as we said, okay, these are remnants from this war. Somewhat more. Okay, so it's typically here that the transformers, people have to look into that from the seismic point of view, and they must block them, or they must attach them with some brakes here to the rails, or anchor them in a proper way, not that we have this, let me say, derailing, and the derailing may also cause to leakage of the, let me say, hazardous oil in these transformers. Okay, this is just some building downstream of a dam. Okay, it collapsed here. We see here the dam is just in the background. Okay, this is a view of a power plant. This is just downstream, maybe 200 meters. And this is a switch yard, which I've shown. Okay, it's not so sharp with some buildings. When we were there, because most buildings were damaged, we were staying in some containers. Okay, you see, this is how it looked at the dam site. The buildings belonging to this dam. Basically, all these warehouses and so on, office buildings, they were destroyed, and here's some village of people working on the dam site. Most of the people actually were living there. They were killed, basically. Okay, we see here some more damaged buildings at the dam site. This is a little downstream, is an access bridge. Buildings damaged. Okay, now after the earthquake, this dam, the damaged dam, had to be strengthened, and it was strengthened by rock anchors. Each buttress, it was about 20 buttresses, each buttress was provided with, as you see, 12 rock anchors, and they were pre-stressed, or the capacity of these rock anchors was about 100 meganewtons per block. Okay, so the critical failure, which I have shown before, was basically at the kink. So therefore, it is anchored below this kink zone or the damage zone in order to increase the vertical stresses. But as you can see here, cross section is quite large. So if you use 100 meganewtons, and the area here is maybe 200 square meters. If you would take a section here, so the stress here would be 0.5 megapascal or 5 kilos per square centimeter. So the additional stress by this, let me say, the additional vertical stress by this rock anchors increased the average vertical stress by, let me say, 0.5 to 1 megapascal. And of course, that increases the shear resistance of of a fractured lift joint. So that was what was done in this case to increase the shear resistance of this crack. So for this work, a lot of drilling work was being done. The repair costs were about $20 or $25 million, which were done then in 1990 and 1991. There were basically two types of repair works which were done. Number one, there were these anchors, which I've just shown, and the other was the leakage. The repair of the leakage was by grouting some epoxy resin, epoxy mortar. This is some work going on. These are, let me say, on a dam crest. These are the locations of the anchor heads of the rock anchors, and here is the equipment used for placing these rock anchors. This here one is already placed in one of these holes. Okay, as you can see here, this is 1991. It's these rock anchors were all placed, as I said, 12 anchors per block, and for each buttress, and in all buttresses, this is just during installation. After stressing, these parts will be cut. Okay, now to make use of a road again. Okay, now for these cracks, as you can see here, this epoxy grouting was being done. Epoxy mortar, it's a special product which is called Rodur, has been used previously in some repair works, also in Switzerland, of crack repairs. And you could see under this grouting pressure, some of this material was coming out. And people were, of course, very much concerned, because 1 kilo of this grout, it costed about $20 or $30. So when they see a lot of material coming out, they were thinking about money. Okay, we see here some local, again here, where this material was coming out, but here, this joint, there was still some local joint leaking. This is a contraction joint between two buttresses. Okay, conclusions here. What I've always said, earthquake hazard is a multi-hazard, and as we have seen here, the rockfall hazard has been underestimated. In most places, access to dams is a problem after strong earthquakes, especially in mountainous regions. And we have clearly seen that, and I have shown here a lot of photos from rockfalls, which are quite dangerous in such locations. I must say people were also fortunate that due to rockfalls they didn't have larger consequences, as in the case during the Wenchuan earthquake, for example. Now, it is important to note that earthquakes affect all components of storage dams at the same time, and therefore all of them must be able to withstand different levels of earthquake shaking. Okay, so there are some people who believe underground structures are safe. Well, they are usually safer, but as I've shown in a tunnel, for example, the tunnel portals are the weak points, and I would say in tunnels, the weak points are also woes where you encountered problems during the excavation of the tunnels. Okay, these are also points one should have a look at if you check the earthquake safety of such structures. Cracks in concrete dams, I must say, for those who like to do the analysis, I hope you have seen, cracks in concrete dams are discrete cracks. They are not smeared cracks. Okay, let me say, in research people like to work on damage models. That means distributed cracks, smeared cracks. But in reality, you have discrete cracks and they are developing along lift and construction joints. And basically, if you want to really model it more accurately, you would have to model also these lift joints and contraction joints. Okay, and there are some problems we have seen, which we know already from the theory, that locations with sudden changes in stiffness and or mass, especially here the kinks and corners, are locations with stress concentrations. You do not have to do analysis, okay, because some people using finite element analysis, if you use, I have shown that before, but I would like to repeat it again. If you use coarse meshes in the finite element mesh, you cannot find out the stress concentrations. So therefore, some people like to use coarse meshes, and therefore their stresses are small. But we know from a theory that at these kinks, if we do a rigorous analysis, these kinks give infinite stresses. So if somebody says he has no stresses, okay, he is just overlooking it. The next point, it must be possible. It is important, I must say, this is again a word for low level outlets. It must be possible to lower a reservoir after a strong earthquake in order to increase the safety of the damaged dam, because it is clear if you lower the reservoir, the water load on your dam will be decreased, and therefore the structural safety, or let me say the stresses within, will decrease. But also, if your reservoir is lowered, you, in a case of a catastrophic release, much less water will be released, and the safety of the people living downstream, of course, is higher. Furthermore, as I mentioned also, to control the reservoir after a strong earthquake, spillways and low-level outlets must be operable afterwards. If this is not the case, I have shown some examples, the dam would be overtopped. And you have seen here the intermediate level spillway, for example, was not functioning, but the morning glory spillways were still okay. Hydromechanical and electromechanical equipment of spillway gates and low-level outlets must be capable to withstand the ground motion of a safety evaluation earthquake. Because it must function after the earthquake, it must be possible to operate some of them, to release the water, to prevent or to protect the dam from overtopping, which is the most critical, of course, for embankment dams. Now, as we have seen here, from the intermediate level, it is probably the first case where, due to hydrodynamic pressures, actually a radial gate was damaged. So the hydrodynamic pressures are not just something theoretical. In some, let me say, unfavorable situations like here, it caused very high axial forces in the arms of these radial gates, which caused inelastic deformation. So it means the forces have been really very large. Okay. And it has to be assumed that the powerhouse is out of operation after strong earthquake. So you have to assume that you cannot release water through the powerhouse. So you need a special device, that means a low-level outlet, to lower the water level. You cannot count on your powerhouse. And as I've shown, the transmission towers are basically weak elements. And if the transmission tower fails, basically it shuts down the power plant. So that is my first presentation, and I would like to go right to the next one. And I would like to, let me say, originally I planned to start with, let me say, dam heightening, but instead of that, because it takes about 1 hour, I would like to first go to that, talk about dynamic analysis of a gravity dam. Okay, so I would talk about this issue first. Okay, and here I would like to talk about dynamic stability analysis of a gravity dam subjected to a safety evaluation earthquake ground motion. I mentioned already, okay, if we have, let me say, the safety evaluation earthquake, like in India, in the Himalayas, you will get high accelerations, 0.6, 0.7 G, peak ground accelerations, I would say. So therefore, you can expect that you have some inelastic deformations taking place, or that you have stresses in your dam which exceed actually the critical stresses are the tensile stresses which exceed the dynamic tensile strength of mass concrete. And I show this as an example. I would like to use as an example a dam in Turkey, which was completed recently. But just to explain once more what I've said again, just to explain what is the, let me say, the concept which we use. We assume that we have cracks developing in concrete dams, and we assume that these cracks develop along horizontal lift elevations, as we experienced here during the Manchil earthquake. As I've shown there already, but this is just a justification of a mathematical model which has been used for a safety evaluation. It is based here on the observations, basically, which have been made during the Manchil earthquake. Okay, we have these cracks upstream, again over the whole length along lift elevations. We have cracks at kings, and we have here blocks which are formed, free blocks formed by cracks along lift joints and along construction joints between the web and the buttress head. Okay, I've shown this here already, how cracks could develop. So therefore, for the safety evaluation of a dam, okay, there are two or there are several approaches. But one approach is researchers look into the formation of the cracks and the crack propagation. Okay, this is one issue, but our assumption, or based on this observation, is it is better to make a conservative assessment of the safety of a dam, assuming that the cracks have already fully developed. So we look into the post-cracking safety of a dam, and we do not really look into the process of formation of cracks, which is a very, let me say, which is a very difficult task. I must say it is beyond what civil consultants can be doing. So therefore, from a safety point of view, it is better to be on the safe side, if I may call it like that, to assume that the cracks have already fully developed. That based on the case of a Manchil earthquake, we could see the cracks after a short time. After a short time, during this earthquake, the cracks have been fully developed from upstream to downstream, and therefore what is relevant is the dynamic stability of a dam of a crack dam is a post-cracking situation. So if we do some inelastic dynamic stability analysis, it is the best, in my opinion, or I would say the analysis is also straightforward. If you look in the post-cracking safety, seismic safety of the dam, and not focus on the development of cracks, which is highly, what shall I say, is still people are not really able to do that. And what we have seen here, based on the Manchil earthquake, is that the weak points are lift elevations and construction joints. So therefore, these cracks will likely develop along those. Now, if we look into the dynamic stability, we look into, let me say, kind of failure modes, which we also consider for static stability analysis. Static stability analysis is basically sliding stability under water load. So depending on your dam, if you have upstream, let me say, if you have a slope like that, this would be favorable. It stabilizes a movement here. This one would be downslope sliding. It is unfavorable, and of course, the failure must not always be along the dam foundation interface. It could also be along weak layers. If you have some thin clay layers, which would be critical for sliding movements in the foundation. So you would have to look into these possible failure modes. These I would call are global failure modes, which are used in a static analysis. And of course, in a dynamic analysis, you must also look into them. But in addition, you also have to look into other failure modes, which I'm explaining here. Now, what is the, let me say, the procedure, or what are the basics of this analysis? Number one is what I've shown at the beginning. It is the experience from Cepheid Root Dam in Iran. Secondly, just as a repetition, cracks develop from upstream to downstream phases, preferably along horizontal lift elevations in a dam body. Cracks originate at locations of stress concentrations. That means the kinks and discontinuities. And four, we have an interface along the dam foundation contact. Many people are focusing on that for the global stability, as I've shown just before. And in addition, you have to consider sliding surfaces in the foundation along discontinuities or weak zones. I would say, the most critical discontinuities in a foundation is if you have some thin layers. Actually, it could only be in a range of even a few millimeters. If you have clay layers, and if you do some drilling, we had some case in Laos like that. If you do drilling and if you take cores, and if you have a thin, let me say, clay layer, if you take the core, you may not get it, may be washed out somehow, and you may find it is just some discontinuity here. But if it is filled by clay, it will greatly affect the sliding stability. Well, it is quite tricky also, let me say, to find fine clay layers, and it was there in a sandstone, siltstone, mudstone formation, where such kind of, let me say, clay layers were found. And at first they were not found, but later on, with some more sophisticated equipment, it was found, and it has led to a change of an dam type from a arch gravity dam to a gravity dam, actually. It has some consequences, some small layers. Okay, what is a methodology which we have been using for this dynamic stability analysis? The first step, usually in a dynamic analysis, you do a linear elastic dynamic analysis of a two-dimensional model of a gravity dam, assuming this is let me say the simplest assumption, assuming incompressible water and massless foundation, and if it is a gravity dam, you assume to have a plane stress condition in a dam body, and you assume you have a plane strain condition in the foundation. Okay, this is just for those who do a two-dimensional finite element analysis. Number two, based on a linear elastic dynamic analysis, one is calculating from this analysis, one is obtaining the time histories, acceleration time histories of the horizontal and vertical earthquake components. And if you do this calculation, you must calculate not the relative acceleration. Some people may have some problems with that, but you have to calculate the absolute acceleration. Because if you have inertial effects on a dam body, it is not a relative acceleration, it is the absolute acceleration. Okay. So as a reference, if you use inertia effects, you are always only interested in absolute acceleration. Number three, one has to define when critical concrete blocks based on the geometry of the dam, location of crest spillway, and the results of dynamic analysis, besides the global failure modes which I have mentioned before, which are used for the static stability analysis. Now, we have done that in India, let me say, sliding block analysis with a computer program RSDAM. It is a freely available computer program which is doing this dynamic stability analysis, and we have done that. It is already a long time ago. I must say, with NHBC, Mr. Chowdhury has done it for the Dibang Dam. We have done that, I think 2006, 2007. It's already a long time ago. This analysis, I must say, he was able to do it in 2 afternoons, really fast. So don't think that this nonlinear analysis is too difficult. Actually, it is the opposite. If you use this, let me say, let me say, dynamic stability analysis, he was able to do it in just in a very short time. It took more time to do this linear elastic analysis and so on. But the inelastic analysis as such of detached blocks, it was possible to do it really extremely efficiently. So if you do that, I would say I also recommend you to do that. Now this is the dam which we looked at in Turkey. You see it's about 160 meters. I always thought it is about 190 meters, but it is a massive gravity dam here, and it is clear that the failure modes are, the static failure mode is along this dam foundation interface, and I will just show some results from the dynamic analysis. If you do the dynamic analysis, here the dynamic analysis was done by, let me say, a spectrum match. The spectrum here, 10,000 year spectrum, we have determined it is in Turkey. We have taken it from a Turkish earthquake code, extrapolated, and we have estimated also on seismic hazard map. We didn't have a return period of 10,000 years, but we have return periods of 145, 475, and 2,500. So we could extrapolate to 10,000 years. Also, it was not possible, so we estimated about 0.8 G. It is not too far from the North Anatolian Fault, which is a major fault line in Turkey, similar to the San Fernando fault in California. Okay, so for the analysis, we have used fully synthetic acceleration time histories as shown here. With a peak ground acceleration, it is here 0.8 g. So we have done, and it fits, this time history fits this acceleration spectrum. Usually this acceleration spectrum comes from a seismic hazard analysis, and rather than synthetic acceleration time histories, people like to use the recorded acceleration time histories, which then are matched or modified in a way that they match this target response spectrum. That is the procedure which is being done. So for this dam, the finite element model was used, like shown here. 2D analysis, of course, the full reservoir is not shown. If you assume incompressible reservoir, the effect of a reservoir can be accounted for by an added mass distributed along the upstream face of the dam. And in addition, it has been assumed that we have a massless foundation. Yeah, it simplifies the analysis very greatly because the ground motion along the foundation boundaries is constant. So it is, and it is the same on the surface and along the boundaries. So it really makes the analysis simpler. I must say, for the seismic safety checks of all dams in Switzerland, basically these two assumptions have also been made and they have been accepted by the authorities. Now, based on this dynamic analysis, we get the acceleration. Sorry. We can calculate the acceleration at the base, and we can calculate at the crest, and we can calculate at each elevation. But what is shown here is just the accelerations. We have about 0.8 g. At the base of the dam, it is also about 0.8 g, 7 meters per second is about 0.7 g. It is slightly smaller due to the eigenfrequency of this structure. And if you look on the dam crest, you see the acceleration is about 35 meters per second square. This is about 3.5 g. Okay, so compared to the base acceleration of 0.8, 3.5 is an amplification factor of about 4.5. So the peak acceleration, horizontal peak acceleration, is about 4.5 times as large as that one of the foundation. So we have the amplification factor of 4.5. So that is just the result of a dynamic linear elastic dynamic analysis. Now we have to select some critical blocks and uplift pressures, and we have found, okay, the first one is the global stability, which is done already statically. We have looked into that, but in addition, from a dynamic analysis, I mentioned already, we found the acceleration here is 4 to 5 times as large as in a base. So therefore, there are blocks near the dam crest which have inertia forces, which are 4 times as large, 4 times larger than those at the base. So therefore, most likely we have some blocks here which will destabilize, and we can have also some larger blocks. We have assumed that we have a crack along a lift joint from upstream to downstream, and we looked into the stability basically of 3 blocks, or I present here just of 3 blocks. One is near the crest. Okay, so this block, it is 318, it is 17 meters high. The other is, as you say, is 37 meters high. Okay, we have considered two blocks, 20 meters higher. The width here is 13.9 meters already, the dam thickness, and at this elevation it is 30 meters thick. Okay, in addition, if you do some stability analysis, it is very crucial what kind of uplift pressure distribution you're using. Here, for the static load, we have a grout curtain here. You know, the effect of a grout curtain is, and with a drainage layer, it reduces the uplift pressure by about 2/3, as we have used this kind of model of uplift distribution, which is used also for the static load combination. In addition, we also have assumed if this crack here develops, water may seep into a crack, and it may develop, let me say, a standard triangular uplift pressure distribution with zero pressure, of course, at the free surface. And similarly, we have that at this location. So we considered the case here for the upper blocks, they were called block 2 and block 3. We considered two cases. One case with full uplift, that means the triangular uplift. Also, this crack may open only during a few tenths of a second, but it is questionable how much water actually can seep into these cracks in these small time intervals. Therefore, this is a conservative assumption that the full uplift pressure may develop, and we also have looked into a case where we have no uplift pressure. What is the effect? And in a dynamic stability analysis, we are interested in calculating the deformations, the sliding displacement of this block 3 or of this block 2 or the global stability in the downstream region of a whole dam body, to be consistent also with the stability analysis of for static loads. So that is a basic assumption. So what we have been doing is a dynamic stability analysis of these blocks which are assumed to be rigid. Once we have cracks developing here, the displacement of this block here, I would say, are 95 or more percent are due to deformations along this crack, and not due to elastic deformations of this dam body. So therefore, we can simply, in this analysis, we can assume that these dam bodies basically are rigid bodies for the dynamic stability analysis. Okay, now these are kind of the analysis for, according to ICOLD, for the dynamic analysis of dams, you should consider 3 earthquakes, and that is what is shown here also. They are called with LC load combination 2, 3, 4. It just means they are 4 different earthquakes which fit the same target spectrum, I must say. They are not the same time histories, but they fit the same target spectrum. And we assumed here, I must say, also in this analysis, is a question with material properties. What is a friction angle of concrete, friction angle between rock and concrete, and between concrete and rock and concrete? And here we have assumed 37%. I would say if you would do some plasticity theory, you would get some residual values, which are maybe 37 degrees, where we know the friction angle depends also on the stresses, but by increasing stresses, basically the friction angle is decreasing. If you have only low stresses, the friction angle may be 45 degrees. But some people like to work with 45 degrees, but I think Okay, we have done it for 37 degrees as a reference, just to see if the dam is still okay or not. But what we can see here, this is the global stability of the whole dam body, and you could see that under this earthquake action, which has a duration of strong ground shaking, we could say is from 5 to 20, about 15 to 20 seconds. It deformed, it displaced, was sliding about 90 centimeters or 1 meter. So the whole dam body, that means the safety factor, of course, is less than 1. You know, if you do global stability analysis and pseudostatic analysis, you would arrive at safety factors. Usually your objective is to arrive at safety factors larger than 1. But here, once we have sliding, that means the safety factors drop significantly below 1 during a short period of time. And since the water pressure is acting permanently, we have a movement occurring only in one direction. So it is a kind of progressive movements here, and it gives typically curves as shown here for gravity dams. Now, this is a kind of sensitivity study. We always propose, I just had at the beginning some discussion, shall we make in situ measurements? Some properties are difficult to get. You may refer to the literature and to make some assumptions here. And if you are not sure, you basically do some sensitivity study. And here is this sensitivity study. We see for sliding movement, of course, the key factor is the shear strength. We have assumed here 37 degrees. All analysis we have done with that, it gives a displacement of about 1 meter. If we increase it by 3 degrees to 40 degrees and 43 degrees even, it reduces to 1/3. So a small change in the friction angle here, 6 degrees, has a quite significant effect. An increase has a significant effect on the sliding displacement. So if somebody wants to do to show that his movements are small, he may use 45 degrees or more, then he would get maybe only 20 centimeters instead of about 1 meter. So a key factor here in this dynamic stability analysis is this friction angle, and it is not really known. Okay, so please keep that in mind. It's very sensitive. Now we would like to look into the different blocks at the top, and I have given the definition of these blocks. This is a block 3. This is a top block, which we are looking at here, and in the top block, please look here. It is without uplift. It's a dry joint. And if we look into that, we can see for now it's a 37 degree. We have a movement, displacement is 2 meters. The base movement was about 1 meter. Now this block there before dry is 2 meters. So it is obvious that for the safety of this dam, actually the stability of blocks near the dam crest are more critical than sliding movements of the whole dam body. But usually people are only doing the stability analysis, global stability analysis of the whole dam body. But critical are actually those near the dam crest. And this has also been shown on the observations made during the Manchil earthquake in Iran, which I've shown before. Okay, we see it also shows that the acceleration time histories, they have also quite some effect here. Some are similar, but one deviates a lot. So if In a nonlinear analysis, I must say, if you do an assessment of the safety, if you do only 3 analyses, you have to take a maximum. But according to some codes, if you would do, for example, 11 analysis, you could use mean or mean plus 1 sigma response values rather than the maximum. But this is for building structures, not for dams. But in dams, we basically say you should at least 3 is a minimum of acceleration time histories, and these acceleration time histories are sensitive, let me say, especially in nonlinear analysis, as we are explaining here. Just to go through that. Again, this is a top one with the effect of the friction angle. Here, the effect of the friction angle is not that pronounced because the accelerations are very high. But if the accelerations are not too high, like the foundation, like the global stability, the effect is much larger. But you can see here, 37 to 43 degrees, it varies between 2 meters and about 1.5 meters. So the difference is only about 25 degrees, 25%, whereas in the previous one, it was more than 2/3, more than 60, 70 degrees. Okay, now this is a block 3, which is also near the top, but which is higher. And we see even for this higher block, we get accelerations of, we get movements of 1.6 meters. The top block was 2 meters. This is already big values, you know, it's not small. So this is block number 2. And if you do a sensitivity study here, because for block 2, the average acceleration is smaller than that for block 3, which I mentioned before. So therefore, also the effect of the friction angles in this sensitivity study is larger than for the top block. What we see here, it varies from 1.6 meters to about 90 centimeters. Okay, about 40% difference. In the previous one, it was only about 25. So this just shows you a critical issue is this friction angle, and therefore, if you do not really have the information on that, you have to do some sensitivity study. Just to remind, we have shown the movements of the block is a crest block, this is this intermediate block, and this is the global stability. Here we got 1 meter, here we got 2 meters, and here we got 1.6 meters, and these would move in the downstream direction. Now the question is, of course, is these values, are they a lot? 2 meters, if I may say, if you look in a stability, the thickness of a dam here is about 14 meters. So 2 meters movement out of 14 meters is basically, if you look into the stability, sliding stability of this part, if we have a reduced contact area, it is still sufficient. It satisfies, after the earthquake, the displaced block satisfies actual static stability factors for sliding and overturning. Now, I would like to give a summary of a sliding block stability. I cannot show here all the results, but I want to show a little what is the sensitivity and what are the critical factors. What is used, I have not written it. The results I'm giving here is for 37 degrees, for a friction angle of 37 degrees. And we consider 3 types of earthquakes, load combination 2, 3, 4. And this is the different blocks. We consider 2 cases with uplift, without uplift. The diagrams I've shown before were all without uplift. Now we get for block 3 if I recall once more results I've just shown for load case 2, basically we get displacement of a top block, is a block 3 of about 2 meters. For block 2, which is 20 meters higher, we get typically about average about 1.5 without uplift. But if we look now with uplift, with a triangular uplift, which is a conservative assumption, we will get in block 3, we get an increase from 2.1 to 2.9, about 40% increase. And here the same, it is 40, 50, yeah, 40% basically increase in the sliding displacement if we take into account the uplift pressures. And for block 2, we see the increase is here even larger. Suddenly the block 2, because we have a higher uplift pressure here, the movement here become about 4 meters. So the critical block for, let me say, dry joint will be the top block. But if we consider the uplift, basically the block 2 will become a more critical one. And we have seen already for the foundation, for the global system, we got about 1 meter, taking into account the uplift pressures. So the uplift, as you can see here, it plays a very important role. It can increase the or reduce the sliding stability a lot. And if we reduce the sliding stability, it means the inelastic deformations, sliding deformations will increase. So this is this brief summary. Now to come to the conclusions, or let me say first to some recommendations for reduction of sliding movements. I would say a provision of shear keys between adjacent blocks over the height of a dam would, of course, prevent the relative movements of such blocks by 2 meters, as I have shown here. Okay, so therefore, if we today in an earthquake area, I would say if we want to control such kind of failure modes, because here in this 2-dimensional model, it has been assumed that contraction joints, the block joints, are basically open, are free. They are not creating any friction resistance. But by providing shear keys, of course, relative blocks could not move. They could only move within the tolerances of the shear keys. Okay, and number 2, one could work on the grout curtain. The grout curtain down inside the uplift stability. Number 3, one could do some improvement and control of the efficiency of drainage system to minimize uplift pressures. I still remember from Dibang, according to the Indian codes, you have to assume that your drainage system is out of operation. That means you have a full uplift along the dam foundation contact. This we consider as a really extreme case. This is a worst case. But in Switzerland, even under the worst case, we do not have to assume that to occur at the same time. You know, if the let me say drainage system is people have not maintained that, then this situation may occur. But in our case, we assume that the drainage system is in operation when this worst case earthquake occurs. But in the Indian code, you go even further, at least at that time, that you ask also to look into the stability, assuming that the drainage system is out of operation. It has an essential, yeah, it has an important effect, as I've shown here in some of the results. Number 4, enlargement of a wedge at upstream heel of a dam to increase the shear resistance. Okay, it also reduces, let me say, the stress concentration at the dam foundation contact, and we could provide, which is being done by some dam in Turkey and in Chile, to provide a so-called seismic belt. This is a reinforcement of a crest along the dam axis in order to minimize the relative movements of blocks. But it is easier, in my opinion. It's simpler to use shear keys, because if you have a reinforcement across joints, you have a problem with corrosion. Okay, you have a corrosion protection problem, and if you have relative movement, it gives also some local damage of the concrete. So, but it has been done for very few dams the dams were arch dams, but it could be done the same for concrete dams, for gravity dams. Now, what is of course easier would be the installation of a geotextile, geosynthetic material at the upstream face of a dam, where cracks along horizontal lift joints are possible, in order to eliminate any uplift forces acting on detached concrete blocks. So here, yes, the geotextile would be useful in order to reduce, let me say, movements of blocks during a worst-case earthquake. We have seen for block number 2, with uplift, it gives displacements of 4.4 meters, but without uplift, it gave only about 1.6 meters. So if you would do a geotextile at the possible locations of that sliding surface, it has a big effect on the sliding movements. The next point would be, one could also increase the slope angle towards downstream of lift joints. Usually it is not being done, but we could do that in concreting, to have the lifts not horizontal, but slightly inclined towards the upstream. That is the equivalent to increasing the friction angle. The slope, the friction angle would be increased by the slope angle if you would not put it horizontally. Now, most of the measures listed above could easily be implemented and would lead to a significant improvement of the seismic safety of the dam, if the safety of the dam is characterized by the displacement, which is the case. So these are the recommendations and conclusions which are made here. I would say the time is just okay. So if you have any questions, please feel free to ask. So this dynamic inelastic dynamic stability analysis, I would say, is a simple type of nonlinear analysis, and I would say most people would be able to do it, and we have done it, as I said, many years back for the Dibang Dam. And I would say, if you have large gravity dam to do safety check, I would say if you would do it in this way, you can make an assessment. It is clear that if you have a movement of 4 meters, the dam will not fail. This is, of course, the objective, but the dam will be damaged, and the water level, it would be necessary, if you allow such kind of displacement, that the water reservoir level can be lowered after this earthquake, and that the top portion of the dam somehow has to be repaired. So again, the bottom low-level outlets are really very crucial in the case you allow for inelastic deformations of the dam under the worst-case earthquake excitation. Yes, if you have any.
Yes, sir. One question. Yes. Sir, at the time of construction of Cepheid Root Dam in Iran, around in 1956, it was started in 1956 and completed in 1961. Seismology was not so developed. Now, in the present scenario, by considering all the factors required to decide OBE and SE, in what category the Manjil earthquake will fall? This is my first question.
Yeah, maybe I answer just one by one. I would say, we would say the Manjil earthquake would fall into the category of the worst case earthquake. That would be the kind of maximum credible earthquake. So therefore, this damage actually which occurred is acceptable under the worst case earthquake, because the reservoir could be retained. People living downstream were not endangered by the dam. So therefore, I would say it has met the objectives of the maximum credible earthquake, but it doesn't mean, I would say, today we do not say that after a maximum credible earthquake, the dam is operable again. It may be necessary after this maximum credible earthquake, if you have severe damage, you must do some repair, or in a worst case, if the repair is too expensive, you may have to lower the reservoir permanently.
Yes, sir. In that case, if we consider it as SE, say MC, whether the dam design was okay, as no sudden water release from the reservoir was seen.
Yes, it will. In this sense, it would be okay. So this damage which has occurred there would be within the acceptable limits, because the dam has been safe after the earthquake.
Okay, sir. Thank you.
But some people have problems to understand that. But this is the maximum credible earthquake, and in most cases, of course, the maximum credible earthquake may never occur. The Cepheid Root Dam up to now is a worst case worldwide, I must say. So there are not many concrete dams which have been subjected to that large earthquake.
So sir, in that case, can we conclude that on which parameter this Cepheid Root Dam was designed is okay for design the safe dam?
Yeah, okay, not really. It is like that. I think originally the dam was designed with a seismic coefficient of 0.1. In a revision after the construction, I think the seismic coefficient was increased to 0.25. And if you do this analysis, the pseudostatic analysis with 0.25, people were able to show that the stresses are within allowable stresses. So if you do the pseudostatic analysis, your conclusion would have been this dam would have been undamaged. You know, for its design, but we have a lot of damage. So therefore the method is not okay, because you would have predicted it to be undamaged, because it satisfies the allowable stresses and everything. But it is damaged, but it is still safe. But it does not mean, that is what I mentioned, the dams which have been designed with the pseudostatic method, we do not really know what is their safety with respect to the new modern methods which we use. And I would say in the pseudostatic method, all these dams have been designed or declared as safe, uncracked, undamaged. But actually damage occurs, and therefore we also need some assessment of this possible damage which may occur.
Then we conclude that pseudo-static method is conservative, because it has sustained the SE or MCE?
Yeah, we do not really know. Okay, I've given a previous case from New Zealand, you know, where we had this spillway lifting structure on crest of a dam, where based on a pseudostatic analysis you used 0.1 G, but if you do dynamic you got almost 2 G, 20 times more. So this would be actually when there are some components which would be unsafe. But we would have to check. Some could be safe. We have done a safety check of 200 dams in Switzerland, and they were also designed for pseudostatic tests if they were redesigned. And basically only few needed some strengthening, and those which need strengthening had already some other problems. And I think in India you have plenty of dams. You also have quite a few dams which have already, under normal conditions, some problems. So if you would add the seismic effect, these problems would amplify, let me say like that. This would be the prime candidates for doing some upgrading then, or which would not satisfy probably the safety criteria.
Okay, thank you.
Okay, Dr. Wieland, this is Dr. I.D. Gupta. I have a question about this dynamic stability, in which it has been assumed that the lift joints have no strength and the crack is already existing. So how realistic it is?
Okay, I would say realistic. We have referred to the observations on the Manchil earthquake. Okay, so there is this observation that the cracks are developing from upstream to downstream through the whole dam body. So we assume that we have that also in other dams, and we look into the dynamic stability of the post-cracking behavior or the dynamic behavior once these cracks have been fully developed. Of course, one can do a lot of research on that. We have not really assumed that the strength is similar. We still have assumed that the friction is there. The main resistance there is the friction at the interface. So it is like a rigid body stability analysis similar to that one proposed by Newmark for the slope stability. So we just applied this method basically to concrete dam. But I would say based on the, let me say, Cepheid Root experience, we can say once a crack starts, because the tensile, I would say probably the tensile strength there has only been 0.1, 0.2 megapascal, very small. So if you have some small tensile stresses, it just propagates through the whole dam body.
Yeah, so if the crack has to develop and propagate, then it may not start deformation or displacement from beginning of the excitation, because the crack will be developed after some excitation, and thereafter only the displacement should start. So in that case,
Yes.
the displacements may be lower than what you have shown.
Yes, this is true. Okay, it depends on the duration of strong ground shaking. I mentioned always that in the inelastic deformation analysis, the duration of a strong ground shaking is a key issue. It's actually even more important than the peak ground acceleration. If you look into these damage processes, you are fully right. But I said we look into a conservative approach, assuming already the crack being developed. So we would be on the safe side. So if we can show that under this, let me say, conservative assumption, the dam is still safe, we do not have to answer these difficult questions
Very true.
which you asked.
Yeah. And this angle 37 degree, which you have shown, is it corresponds to the dynamic friction?
Yeah, well, it is the residual friction. Okay, because we have a peak, you know, with the cohesion or tensile strength, and basically we have then some crack roughness and so on. So there have been some tests being done, I think, in Montreal, but some on mortar, and they have shown even very small friction angles, even smaller than 37 degrees on model tests in Montreal.
And
So
under dynamic
therefore,
condition, it may further be lower.
yeah, if it is lubricated by water, you know, if it would be, if it is mortar, but here we have concrete, so we have some aggregates are quite large, let me say 5-10 centimeters. So we have also some interlock, and they have some roughness and so on. So this is, I said, we have quite some uncertainties. So therefore, we also propose to do this sensitivity study just to know what could be the possible effect.
Yeah. Okay. Thank you.
Okay. Are there any more questions? Ms. Kalpana, I think if it is not the case.
Yes, no, then we can break for lunch, sir.
Yes.
I think we can break for lunch and reassemble at 3 o'clock.
Yes, it's fine.
So we'll close this session.
Yes.
Thank you.
Okay, welcome.